Hello and welcome. This is Late Night Code. My name is Ian Riley, and I'm so excited to be finally bringing you another episode. So, a couple of weeks ago, we had some really exciting news in the household. My wife delivered our third child, a baby boy named Joseph, and it's been a real joy to have a newborn in the house. So, we've loved it, but as you might expect, the routine has definitely been thrown off. We're a bit more on the sleep deprived side now, and we're just trying to figure out what our new normal looks like. And with that, we're trying to figure out where time goes for work, where time is for family, how we can support each other through this. And of course, when do we make recordings, right? So those are the things we're trying to figure out. And it's mean, for example, that I didn't get to upload a recording this past Friday. That just kind of comes with the territory. But I think we're getting close to a new normal and starting to find some time for recordings again, which is really exciting. In this episode, we're going to be looking back to the restaurant opening problem. This is a problem that we worked on this past Wednesday, in which we were given a grid. We had to solve for a minimum cost given certain restaurant locations, and we were actually able to use a brute force solution to solve that particular problem. The brute force solution came out to like an O of n to the fourth, which is really not great, and it's not what we want. But n was constrained to about 50, and so it's so small of a number that even 50 to the fourth is really not a big deal. And so the brute force solution did in fact work, which is also part of the reason why that problem is listed as an easy problem in that regionals contest. But what I thought would be really fun is to revisit the problem and see how we can actually improve our algorithm in order to get the best performance that we can get. I thought that would be kind of fun, and that's what we're going to be doing in this episode. On a related note, I've been reviewing the analytics from the channel. We've only been going now for a few weeks, and the restaurant opening has acquired more views than any of the other episodes combined. Now, it's only about 50 views, but that's still a lot for this channel, and it's the first time I've ever gotten so many views on a video, and I can't tell you really in words how excited, how encouraged, and how heartwarming that was, to have happened. So it's been really amazing to see that people are seeing the content, that they're watching the content, and I really hope that you're getting something out of it. So if there's more that I can do to improve the content of these videos, please let me know in the comment section below. I'd be really happy to continue to work on them, and I hope that they'll continue to attract more views because I'm having a lot of fun with it, and I want more people to have fun with it too. So anyway, that's been really, really great. And just again, I'm so excited to have you all here with me, and I'm looking forward to getting to do more cool things. But with that out of the way, right, I can talk forever. Let's start jumping back into this problem. So here we are on Excalidraw, and I'm going to go ahead and talk just real quick about our prior solution to this problem. But let's just go ahead and keep it short and sweet. So we start with a 4x4 grid. In the particular problem, grids can go up to about 50 by 50 in size. They can also be rectangular. They don't have to be squared. And what we're basically asked to do is to go ahead and select a cell. And then let's go ahead and just select the very first cell of the grid. And then we're asked to compute a cost associated with that cell. Now, the cost associated with this cell is to first assume that every cell has a weight. They give us the weight. So this cell would have a weight of G00, and then this next one would have G01, G02, and then G03. The notation there being one where we use G, and then followed by the row and the column for their subscript. And then effectively what happens is we take these weights, and then we have to compute a Manhattan distance for each of these particular cells. So the Manhattan distance that would be associated with G01 would be 1 because they're on the same row, but they're separated in column distance by 1. G02 would have a column distance of 2, and then G03 would have a column distance of 3. And so what happens is we can take the Manhattan distance, multiply it by the weight of that particular cell, and then sum those products over all cells in the grid. And so then if we were to consider again the accumulation of all weights multiplied by their Manhattan distance to our target, that is the cost associated with that particular cell, which we're just going to go ahead and quickly call F00, foo, right? And then what we want to do from there is just find the cell that has the minimum such cost. Okay. And the way that we approached that in our last solution was to actually just do this approach of taking each candidate cell and then looking over all of the other cells to figure out what the cost is and then just choosing the minimum. And so if we were to mathematically describe our approach, we would say something like this. We would say that we wanted the minimum, and then we would say for all RC, where RC is a row column pair. And then from that, we would sum up over IJ, which is another row column pair. And then we would calculate here that should be a straight line for the absolute value. We would calculate the Manhattan distance, which would be the absolute value of I minus R plus the absolute value of J minus C. And then we would just multiply that by the weight GIJ. And essentially the issue with this particular approach lies in the description of the for all RC sum over IJ. Because what that effectively tells us is that our approach to the solution has to be a for all rows, for all columns, for all rows, for all columns. And we're told in the problem description that these rows, columns, right, all of these can be effectively less than or equal to n, which is less than or equal to 50. We produce a solution that ends up being O of n to the fourth. Okay, since it's R by C by I by J, all of them are capped by n, so we just go ahead and raise them to n, and so we have n to the fourth here. And the reason why this solution worked is because since n is constrained to 50, then effectively all we're really talking about here is about 6.25 times 10 to the 6, or 6 million. And while 6 million seems like a big number for computers, that's really not a problem. And so our machine can crank through that and solve it in a sufficient time. I think you can solve it definitely within a second, which is usually the limit that we're given. So again, even though n to the fourth seems bad because n is so constrained, it's fine. Now, if n were to be larger, we'd have a serious problem on our hands. We would need a much better solution, which is what we want to investigate in this episode. So now we need to talk about how can we actually take this kind of idea and improve upon our algorithm in order to produce a much better algorithm. Now, I have a standard approach that I take whenever I want to go about improving my problems, right? Improving my algorithms. And I typically follow about 3 steps. So step number 1 is I want to consider the complexity, okay, followed by the coefficients. Now, in academia, which is where I teach, of course, we don't typically talk about the coefficients of our algorithms. So for example, I just mentioned that our problem was O of n to the fourth. I haven't really sat down to look at what the coefficient would be, but essentially the point is that it's not just 1 n to the fourth. There's some coefficient factor by that, right? And so what that means then is for the theoretical complexity, we typically drop that off. Okay, we just say O of n to the fourth, regardless of whether or not it's 1, 5, 10, 100, we don't care. Okay? But I've been personally told that at least in ICPC for the collegiate competitive programming contest, people do actually test for the coefficient factors. So while they're technically taking a side seat to the actual complexity, for example, n squared will always be better than, 3n4 versus 1n4, right? Getting it down to n squared makes a lot more sense for us. But there are certain coefficient factors that people test for. And so if they're testing for something like a 3n squared and we produce a 10n squared, we might actually get a time limit exceeded or fail, because even though we're in the right family of complexity, we haven't hit that right coefficient factor, which again is very different than how we approach things in academia. In academia, we only focus on theoretical complexity, not the coefficient factors. But again, once you find the right family, the right theoretical complexity, then the only other thing that you can do there in terms of its complexity is improve the coefficient factors, right, in order to improve performance. Now, what we have is an O of n to the fourth. Again, I'm ignoring the coefficients for right now. And what we like to do is move to an O of n squared, okay? Now, we haven't actually asserted that we can get down to an O of n squared, but we know that we're working with a two-dimensional matrix. So it's an n by n matrix. And that at least tells us that it's possible, that it might be possible, and it's worth investigating whether we can get down to O of n squared. Now, do we need to go further than O of n squared? Probably not, because again, we're working with a 2D matrix, which means that in order to just process all the data to begin with, we have to have an n squared algorithm. So we might as well, if we find something in that right category, we might as well stick with it. Now, once you've determined that you've hit the right family, the right theoretical complexity, then the next thing that you can start doing to improve performance, which this won't improve performance on paper in the sense that it won't affect the theoretical complexity, but it will overall make your algorithm run faster, is to consider hardware optimizations. Okay? keep in mind that when we actually run our programs, we're running our programs on machinery, and the code that we write is going to be compiled by a compiler, assuming that you're using one, although most these days do. And so what that means is that our languages and their tools underneath provide certain features that can make our code run faster. And the code, rather the machine that that code is running on, can also provide hardware features that can improve the performance of our code. Now, the one that comes up the most often is actually called cache performance, which largely relates to the cache on your CPU. Normally the L1 cache is the cache we talk about. And so effectively what happens is that when memory is loaded, it'll be loaded onto the cache in our CPU. And if our CPU can reuse cached memory rather than have to load it from somewhere else, it's significantly faster. And so the more that we can do to improve what's called the hit ratio on our cache, the better our algorithm will run. Again, doesn't affect the theoretical complexity, but does help the algorithm run faster. Some other things you might hear about would be like SIMD. This has gotten some attention recently. Well, first of all, it's just a good hardware optimization, but Mojo was announced, which is a superset of Python, and they were showing off SIMD instructions in Mojo. So essentially Python would have SIMD then, which is really exciting. And so this is another hardware optimization that's been around for a while, stands for single instruction, multiple data. It effectively allows you to use the same instruction across multiple different data points. So if you wanted to add 4 numbers to 4 numbers, rather than doing 4 separate instructions, you could do one instruction that would add them all. So this is pretty cool. Some other ones you might think about would be things like GPU acceleration. You know, you'll hear about that from time to time, how a certain program is GPU accelerated. That can be really beneficial, especially with matrix problems, kind of like the one that we have, because GPUs are specifically designed to deal with vector and matrix arithmetic. So you can get a lot more benefit off of using your GPU there. So these are some things that you can think about. Now, oftentimes the first thing you want to do is think about these in the context of your language. This is one of the reasons why I was really interested in using Rust for this channel, because when it comes down to competitive programming contests, like what I'm familiar with, you really just want to get the problem solved and move on because you're on a time constraint. But it's always really interesting after the fact to think back and wonder, could I have written better algorithms? Could I have gotten better performance? And I've done a lot of contests in Java, and a lot of times I really just don't want to go back and try to optimize my Java code. And it doesn't feel that fun to do it, if I'm being honest, right? But with Rust, it's a lot more interesting because Rust provides a lot more of the tools that we would like to use in the language to get these hardware optimizations essentially for free. So for example, for cache performance, Rust provides a greater variety of primitive data types, right? To kind of reuse some Java lingo there. And those that variety of primitive types actually allows us to improve our cache performance just by having more specific types for the numbers that we're using. And that's really, really cool. In addition, Rust for loops and Rust vectors can actually auto-vectorize to take advantage of SIMD instructions, which is always a bit ambiguous when it comes to virtual machines, but not for Rust. So this is really, really exciting that we can do just a few minor things and actually see some really good hardware performance for that reason. So I really like that aspect of Rust. It just makes it feel more fun, I guess. It feels more rewarding to be mindful without having to do some really silly tricks that honestly would just be really confusing to read, right? Rust becomes in a way more readable while also more performant. It's crazy. I love it. So then number 3 is going to be concurrency. And in particular, what we're talking about here is really just a multi-threaded, if I can spell, there you go, multi-threaded. So having a parallelized or parallel solution. Now, you do have to be careful when you talk about multi-threaded because normally by spinning up more threads, you can do more work simultaneously so long as you have the cores to support it. And that means you're going to be running multiple factors faster. However, there is performance overhead for spinning up those threads. And so you need to weigh the performance overhead of spinning up the threads to the actual performance gains that you're getting for using them. A really popular library in Rust for parallel solutions is called Rayon. And I believe right now that they advertise about a 2.5 microsecond overhead for using their thread pools. Now, 2.5 microseconds is fairly small, right? Especially if your program is running in seconds. So you're definitely going to see performance benefits if your program is running in the hundreds of milliseconds to the seconds. But if your program is running in the order of microseconds, it might actually be the case that the overhead incurred by the thread pull is effectively too much. Like it's just not, it's just too much to be worth making use of a parallel solution. So just be aware of that, especially with competitive programming problems. You probably won't be using concurrency all that much just because the overhead is too much for the kind of problems we're working on. Keep in mind, again, that usually a problem has to be solved by a second, and some of the more difficult problems, 2 or 3 seconds. And a lot of times we talk about multi-threaded solutions, we're talking about problems that could take several seconds to minutes to solve without a multi-threaded solution. So concurrency is another one to consider, but may not always be the one that's going to help you. And what we're really interested in today is primarily this complexity. We want to see how we can improve the nature of our algorithm in order to get a much better complexity. Secondarily, as it becomes relevant, we will consider in particular these aspects of hardware optimizations. We'll be looking at how we can help the compiler to better utilize cache performance by giving it more strict data types. And we'll try to make sure that we make use of proper for loops and iterators where we can to help Rust auto vectorize our code. But we're not gonna be trying to dive into assembly or things like that in order to see the effects of these things. We're just going to try to give the compiler the best help we can and then let it go from there. And if there's more things that we could be doing, that would be a topic for a later video. There certainly will be, but it's just not what we're going to dive into here, right? It's not really what you would do in a competitive programming environment anyway. Whereas the things we'll be showing off today are things that you could easily do and would be beneficial to do. Okay, so let's talk about this first one. How do we go about improving the complexity of our solution from O to the n4 to O of n squared? Well, if you're ever going to be improving the complexity of your solution, then one of the things that you want to start looking at is where is the repeated computation, right? Where can we start reducing the amount of computation that we need to perform by either condensing numbers or storing numbers or things like that? Usually, if you want to improve performance, you need to learn how you can use memory, right, in order to do that. And so what we need to do here is look at our particular problem to see, again, where is the repeated computation that would allow us to start reducing the performance, because ultimately we have to have a way to reduce out the number of numbers we're looking at whenever we go about computing these costs. And so the first thing that hit me when I went back to looking at this problem is the fact that we have this description right here for our cost calculation. So the cost being the sum over the Manhattan distances multiplied by a weight. And the reason why that caught my attention is because of the distributive property. Because of the fact that multiplication is distributive, we can actually rewrite this cost metric as the row distance, so I minus R, multiplied by Gij plus J minus C, right, absolute value of, times Gij. Which is another way of saying that the cost metric here is effectively the row Manhattan distance multiplied by the weight plus the column Manhattan distance multiplied by the weight. It allows us to separate the ideas of row distance from the ideas of column distance. And why that might be really interesting is because certain elements share a row distance with each other and certain elements share a column distance with each other. And so if we come over here to our particular grid, we can actually see where those elements are, right? So if I were to go ahead and let's go ahead and just take a green real quick here. If I look at all of these elements on the first row, right, if we call this R1, then all of these elements actually share a row distance, right? In this case, a row distance of 0 with that first candidate cell. And if I move now to the next row, all of these share a row distance with each other. In this case, a row distance of 1 to that selected cell, and so on and so forth. The next one would be a 2, right? And so we can go ahead and write that real quick. So this right here would have an I minus R equal to 0, and this would have an I minus R equal to 1, and this would have an I minus R equal to 2, and the next one would be 3. And similarly, if we look at our columns, right, then right here, our first column has a column distance that's shared, and it, of course, is also 0. Our next column has a shared column distance that would be 1, and the next column would have a column distance that would be 2. And so what happens here is that all of the elements in the same row share the same row distance with the same candidate, regardless of where that candidate is. And all of the cells that are in the same column share the same column distance with the same candidate, regardless of where that candidate is. And since they do that, if we think about a lot of these elements having the same row distance, then you'd have G00 plus G01 plus G02 plus G03. And if they all share the same row distance, then that row distance can come out, right? Which means now what we're saying is that this term here that's going to be used as a part of our cost calculation is really that row distance multiplied by the sum of all of the columns, right, of G0J, okay, where it's the 0th row and then it's the jth column. So each of the cells along that, which is another way of saying that if all of the elements of the same row share the same row distance, then you can actually compute the addition that they add to the cost by doing the row distance multiplied by the sum of the row. So now if we come back up to this grid that we have here, if we're trying to figure out the cost of our G00 of that selected cell, what we can actually do now is think about all of the row sums and all of the column sums, where we can take the row sum of the first row, multiply it by 0, take the row sum of the next row, multiply by 1, and the row sum of the row after, multiply by 2. We can take the first column and multiply it by 0, take the second column and its sum and multiply that by 1, and so on and so forth, and just add it all together, and that actually gives us our cost, which is really, really cool. Now, if we were to kind of scroll down for a second and break down what that means, and so these effectively represent the column sums and row sums. And so if we were to go back and calculate F00 here, then the way that we can calculate F00 knowing about these sums is just to say that F00 is now going to be 0 times C0 plus 1 times C1 plus 2 times C2 plus 3 times C3. And then we're going to add to that 0 times R0 plus 1 times R1 plus 2 times R2 plus 3 times R3. And this will actually give us that cost. Okay, so we'd have to sum up all the elements, and then after we've summed up all of the elements, we can then take all of their sums and multiply it by this cost, and that would give us that cost. Now, what happens here is that this is no longer an n-squared cost calculation, because once they've been summed, and we only need to sum them once they've been summed, you only need to iterate over the sums, and there's effectively 2 n sums. So what's happened here is that our O of n squared cost calculation has now moved to an O of n cost calculation. And since we still have O of n squared elements, because we'd have to do this for every element, our solution in total goes from an O of n to the 4th to an O of n to the 3, because there's n squared elements and it's an n cost calculation, so n cubed in total. Now that's not n squared, which is what we want to get to, right? But we are improving upon our algorithm, which is still really exciting. So now the next question is, how do we get from this to now an n squared solution? And the answer is we have to find a way to stop doing a linear cost calculation. We need to find a way to take this cost calculation and move it to O of 1. Okay, so that means that there's more data that we need to be able to store in order to make this work. And interestingly enough, that data is actually right here. That data is F00. Now, how does that work? The way that I can best exemplify this is to ask the question, now that we know F00, what is F01? Okay, so if we're going to scroll back up to our grid real quick, that's G00, which is F00. So what is G01, which is, or the cost associated with G01, which would be F01. Okay, so what is that cost? Well, let's go ahead and break it down. That means that we're staying on the same row, but moving over by one column. So that means that we're going to have F01 is equal to, since we moved over by one column, it's 1 times C0 plus 0 times C1 plus 1 times C2 plus 2 times C3. And then it's still on the same row, so it's still 0R0 plus 1R1 plus 2R2. I'm just going to try to speed things up real quick. And 3R3, right? All of that makes sense. That's the cost calculation. But now let's look at the similarities, right? We know that they're on the same row. And just as we would have expected from them being on the same row, they have the same row sum, okay? Which means that if we're looking at elements on the same row, once we've calculated the row sum, we don't need to calculate it again. It's the same for all of those elements, right? Also, if we look at the particular coefficients, right, the coefficients of the terms that we see for the columns, they're all the same terms, and the coefficients have all changed, right? They've actually all changed by 1 in this case. Although a slight oddball, right, with the C0, of course, because it didn't just go down by 1 like the other ones did, it actually went up by 1. The main point here is that all of them have effectively changed by 1. And that should make sense because we moved one space over to the right, so that means that everything should be changed by 1. Well, now what I'm going to go ahead and propose real quick is I'm going to go ahead and propose a new definition. I'm going to propose that we have some factor g, which is equal to the sum over ij of g ij. Now, what does that mean? That's the sum of all elements in the grid. Okay, that's the sum of all elements in the grid. Well, if that's the sum of all elements in the grid, one thing that we should be aware of is that's also the same as the sum over all j of cj and the sum over all I for ri. Okay, because every column, if you accumulate their sums, is the sum of everything in the grid, and every row sum, if you accumulate those, is the sum of every element in the grid. So these are all the same. Well, now that we know that all of those are the same, imagine for a second that we look at these column values, okay? We look at these column values, and I were to subtract g from those column values, okay? So let's do, real quick, let's do F00 minus g. Now, I'm going to go ahead and ignore the row terms because we know that the row terms stay the same from F00 to F01. I'm just going to focus on the column terms, okay? So that means we have the column terms for F00, and I'm going to use the definition that I stated over here where g is going to be the sum over all column terms. Well, if I'm subtracting all of those away, that means now that all the column terms are going down by 1. So that means that we'd have a negative 1 C0 plus 0 C1 plus 1 C2 plus 2 C3. Now, what does that remind us of, right? If we come back over here now, if we look at F01 and we look now at F00 minus G, look at the terms. We have a 0 C1, a 1 C2, and a 2 C3, right? The same terms. Now, the only thing that's different is the previous oddball, that C0 term, because now it's negative and we need it to be positive. But here's the real kicker, right? We were just at F00, which is in the 0th column, which means that we could have grabbed that C0 value. And in fact, we could grab every column sum as we move over the columns, and we can accumulate them. So imagine then that we have this accumulation of these column sums where we take something like an L here, I'm just going to call it an L for a left-hand sum, and we just have that be an accumulation, and we'll call this Lj. And this will be an accumulation of all J0 less than J, okay? And we'll call that Cj. So it's an accumulation of all column sums leading up to the current column we're at. Well, now let's add to this formula, right, 2L1. So that's the sum of the columns before C1. Well, that would then be now the add of the term to C0, since that's the only column less than 1. And if we add 2Z0 to C0 to negative 1 C0, these cancel to produce F1C1. And then now, isn't that just the same as F01? So now this becomes F01, which means that if we've calculated F00, if we've calculated the cost of the first cell, to calculate the cost of the next cell, all we have to do is take the initial cost, subtract away the sum of all elements in the grid, and then add twice the previous column sums, and we get the new cost. And guess what? That cost calculation is O of 1. So now we have a way to calculate cost that is O of 1. And if we can calculate cost at O of 1 with O of n squared elements, we now have a very, very nice O of n squared solution. It's pretty cool. Now, we should definitely ask, like, does this only work when we iterate across the row? And not true, because in that definition of the G, the sum of the grid elements, we also see that it's the same as the sum of the row sums, which means it has all the row terms. And if we think about moving down a column, then the column terms stay the same and the row terms change, which means that now we'd still be subtracting G, just using the row definition of G, not the column definition of G, which means that F00 going to F01 would mean that you would subtract G and keep track of your column sums. But if you go from F00 down to F10, the next row, you still subtract G, you just keep track of your row sums now as you're moving down. So that's all you would need to do, and it would work the same. And of course, if we can move across a row and also down rows, then we can move down and across, which would allow us to calculate the cost of every element in the grid. So this now gives us an effective formula that we can actually use to calculate the cost of all of our elements in O of 1 time. Now, this does require a few things. It would require us to compute all of the sums, including the grid sum, which is not hard. We can actually do that while we're processing the elements. It also requires us to calculate the initial cost of F00, which actually, again, we can do as we're calculating all of the, or as we're processing all of the initial elements. So what we can do now is whenever we take in our inputs, we're just going to go ahead and calculate all the column sums. We're going to calculate all the row sums. We're going to calculate the grid sum, and we're going to calculate that initial cost associated with F00. And then we can just solve for all of our cells by just using this initial cost and this formula, and then just take the minimum as we do that. And that will produce for us a solution in O of n squared time. And you know, the real kicker in this whole thing too, is that once we've processed all of this, we don't even need the grid anymore. Right now, we're currently using O of n squared memory because we need to store the grid. But once we do this solution, we don't even need to store the grid. Our memory goes from O of n squared now to O of n. It's actually technically it's technically 2n, but it's O of n in terms of its theoretical memory complexity. So not only have we vastly improved the performance of this algorithm, we've also improved its memory requirements, which is really, really cool. So with that, again, if you guys have any questions about that, just plop them in the comments down below. Love to answer them. But with that, I think we are ready to go ahead and jump into some code here and start working on improving our algorithm. Now, we're going to be using a new application today. This is called Alacritty. I've been using this recently. It's built in Rust. It's GPU accelerated. It's available on all of your major OSs, including Windows. And I've been using this in place of Windows Terminal. I'm really, really liking it. I was having some problems with Windows Terminal, and then I found out that the problems were because I configured Windows Terminal to always run as administrator. Don't do that if you're using WSL. WSL does not like it when you do that. So I fixed it, and it's better now, but I wanted to check out new things, and I found Alacritty, and it's been really, really cool, and I'm having a ton of fun using it. So I'd actually really recommend that you use it as well. It's super simple to configure. You just create a YAML file, you put all your configurations into it, and you're off to the races. I mean, it took me about maybe 5 to 10 minutes to get that set up, and then dumped in, you know, Tokyo Night theme. I dumped in all my favorite hotkeys, and I pointed at WSL, and now I've got Alacritty pointing at WSL, and it's been phenomenal. So heavily recommend it. So that's what we're going to be using here now. And we've got algols, and all I'm going to do, go ahead and do here is just open up the previous restaurant opening solution, and we're just going to extend this solution. So I'm going to go ahead here and grab my pub main. I'm going to go ahead and copy everything from there and just paste it down below. And we're going to call this main in2 for our n squared solution. And so this way we don't have to create a whole new file, right? And then we're just going to go through this and start trimming this down. So as we do this, one of the things that we're going to keep in mind is not only our new algorithm, but also ways in which we can help Rust by looking for opportunities to use more specific or more strict numeric types, and also to see if we can better use iterators or for loops when they come up. So first thing here, we have in and m, which are currently i32s, but we're told in the input prompt, again, if you've not seen that video, please go back. It'll go through the input prompt. You can also look it up for yourself online, Caddis ICPC Southeast Regional Contest 22. And what it basically said is that N and M can only be at most 50. So pretty small number. But we also know that N and M are going to be used for the sizes of arrays. And anytime that you're using a value as the size of an array, Rust really likes it to be a U size. So what we're going to do here is we're going to go ahead and tell Rust that these are going to be U sizes in order to help Rust understand our intention. So we're going to have these be U sizes, and that's going to help Rust out. Then the next thing that we're going to go ahead and do here is now process our grid. You'll notice that this is a slightly different implementation than the one we did online. This was recommended by Rustclippy. I heavily recommend that if you're working on a cargo project, you use Rustclippy. So for those who are using this repo, definitely make use of that. It'll help give you good suggestions that can also help Rust auto-vectorize your code. So they're very, very good instructions. But now we know that we no longer need the grid. Instead, what we're going to be calculating here is going to be our column sums. So we're going to have our column sums, which is now just going to be an array of column sums. And so that's going to be, in this case, let's think about what the strictness of this type would be. So every grid cell is effectively a byte. So it's a U8. But then if we can have 50 of those, because the maximum size here is 50. And so that would mean that we would have 50 by 50, so it's 2,500. Certainly larger than a byte, but not as large as a short. So we can have here a U16, and we'll have up to 50 of those. We would do the same thing with our row sums, right? Those would also be shorts. Now, if we were to add up all of those, then we'd have every row sum would be 2,500. There could be 50 row sums, which gets us to about 125,000, which is going to be larger than a U16. And that puts us now into U32 territory. So we're going to have a grid sum, which is going to be a U32, and we'll have that start at 0. We're also going to calculate our initial cost. I'm just going to go ahead and call this the cost I to be associated as a cost with a row, and that will also be a U32, okay? Because our costs can actually get larger than our grid sums, but they won't blow a U32 here. So that's looking pretty good. So now these are the things that we're going to calculate as we're taking our inputs, which means that the way we're approaching inputs now has dramatically changed. We no longer need this loop right here. Instead, all we actually have to do now is just loop over all of the values to n, because we're going to be given n lines. And since we're going to be iterating over a range, this is where it can be really helpful to use a for loop. So we'll say for I in 0 to n. Okay. And then now moving on from here, we're going to go ahead and get a string that we're going to break, and that's going to have m elements. And we don't need to collect that into a vector anymore, so we can get rid of this. And in fact, just rely on this buffer implementation. So we can just go ahead and bring this one back. And since we're going to be using a buffer, we don't need to create one every single time. So we can just bring this out of the loop. And as long as we do a buffer clear on that, we are fine to use it. And actually, I'll just go ahead and clear that at the end, so that, because we know it starts clear. And then we can go ahead and use standard to bring in content into that buffer. We unwrap it if there's a problem. We take the buffer, we trim it, we split it, we parse it. But we did mention that all of these are going to be up to 50. So that means they are effectively stored in a single byte. So again, to help Rust out here, we'll map them into their bytes. And we don't need to collect them anymore, because once we have them, then all we need to do is effectively a for each to process each one. Now, a couple of things though. If we do a for each, then that only tells us what the byte value is. It doesn't tell us what column it's associated with. So you can do what's called an enumerate on an iterator, which allows us to pair the columns. We'd have J here and the byte, which we can call B. Okay. They would call it GIJ. So we'll do that real quick. And then I'm just going to need that pipe. There we go. And so now this will take a closure that will take the index and the actual byte. I'm also going to go ahead and really quickly add a take m, which basically limits the iterator to a defined number of iterations, and that can help Rust as well. And so now we've got this for each loop where we can actually process each of these bytes And we'll just be doing all of the work here to calculate those row sums, column sums, grid sum, and our cost. So now if we want to go ahead and do this real quick, our row sums, which would be associated with I, is going to be plus equal to our Gij as a U16, right? Then our column sums at J will be plus equal to Gij as U16. Our grid sum will be plus equal to Gij as U32. And then our cost at I, again, so this is the cost associated with that very first element on this row, is now going to be plus equal to, and then it's going to be the row cost and the column cost multiplied by the weight. So now we'd have to consider, in this particular case, all of the rows are increasing, and it's going to be I minus 0, so it's effectively just I. So it's I as U32, and that's going to be plus, and then it's going to be J as U32, and then it's all of this, so we can now say all of this multiplied by, and that's going to be multiplied by now this Gij, and that Gij needs to be as a U32 as well. Okay, so that's looking pretty good. We've got the row sum calculation, we've got the col sum calculation, we have the grid sum calculation, and the cost of I by effectively taking the row cost plus the column cost, or the column distance plus the row distance, and then multiplying it by the weight, which gives us the cost associated with this element. So then now, once we get to the bottom of this loop here, I'm going to go ahead really quick and kind of space these out for readability. We're now at a point where we've calculated the row sums, the column sums, the grid sum, and the cost I. So we're actually ready now to jump into our algorithm. So what is that algorithm going to look like? Well, first thing is we're going to have a minimum cost, right? Which is going to start now here as really our cost I, because we've already calculated a legitimate cost. So there's no reason to fake it. So we can just say cost I. That seems fine. And then now we don't need these 4 loops anymore. In fact, we can just use a few loops. We can say for I in 0 to n, for j in 0 to m, and we can get rid of all of the rest of these, right? So now let's talk about how this is going to work. The other element that we haven't accounted for yet is our left-hand sums, our ability to accumulate sums, row sums, and column sums as we move across. And so we're going to need to account for that. So I will need, for example, I will need a mutable, like let's say left-hand sum associated with our I values, which will be a 0 U32. This will allow us to accumulate row sums. I'm also going to need a mutable left-hand sum J, which will also be a U32, and this will be associated with the column sum. So the row sum should be outside the for loop since it's accumulating over rows, and the column sum should be inside the first for loop since it's accumulating over columns. And so this will allow us to keep track of the things that we've been using. So then now what we can do is now we can talk about calculating our cost I associated with every row. So if we were to enter a new row, how would we update that cost? And that comes down to our formula. Earlier, we said that for our formula, our cost associated with I, which is when we move down to a row, is going to be equal to the cost associated with I, so the previous rows, right, plus 2 times the left-hand side. Of course, this is going to be the left-hand side associated with the I, or the row sums. And then that's going to be subtracted. Now we're going to have the grid sum. Okay. So again, so every time we move down a row on that first column, it's the previous row's sum, or previous row's cost, sorry, plus 2 times the left-hand sum of the rows, meaning it's the 2 times the row sums we've seen so far, which effectively allows the prior row sums to keep increasing by 1. And then we subtract away the grid sum, which effectively causes the future or the next row sums to all go down by 1. So that's our cost of I. Now, if we look at this formula, one of the things that we should notice is that the cost of I right now is the cost associated with the first row. And if we subtract away the grid sum, then it will now be incorrect for that first row, which we don't want. It'll be incorrect for all future rows as well. So we would need to augment our loops here to account for that fact. However, I really don't like augmenting the loops and having to add conditional statements into the loops, because it either forces you to add a lot more code, or it forces you to add conditional branching into your loops, where the vast majority of times you'll fail the branch. And so I don't really like to do that. So instead, we'll do a little bit of a hack. I'll go ahead and say that my cost of I is now plus equal the grid sum. Okay. And so avoids, we can say here, avoids needing to use conditional branching in the loops. There we go. And so effectively what happens now is that for the first row, since we've added the grid sum, the cost of I will be now the cost of I plus 2 times 0 minus the grid sum, which means it goes back to that original cost for that very first row, which is exactly what we want. And now with that cost of I, we can now start looking at all of our our iterations of our columns. Now, I can't keep manipulating this cost of I. Oops, sorry, let me move it there. Because I needed to hold the place for that first element of the row so that way I can manipulate it for each next row. Which means that now I'm going to need a mutable cost j to be associated with the cost of this very first element. So we'll call that here our cost of I. So we can go ahead and use that. And so that I can do a similar thing down here, I can now say that the cost of j is equal to the cost of j plus 2 times the left-hand side associated with j minus the grid sum, where the left-hand sum associated with j is now the accumulated column sums. And then once again, I can go ahead and do that same trick where I add in the grid sum, because now the cost of j will be the cost of j plus 2 times 0 minus the grid sum, which means it goes back to the original cost of I, which means that once again it's associated with that very first element. And then now we can update our minimum cost finally. So we can say our minimum cost is equal to the CMP minimum of that minimum cost, and now the cost of j. Technically, cost of ij if we're being really particular, but this is fine. This works for me. And so now we've calculated minimum cost, and then what's left is now to do the updates. And the only update that we actually have to worry about is now that we've processed this column, we need to update that column sum. So the left-hand sum associated with the columns is now going to be plus equal to our column sums associated with j. And then let's see, and so that's going to be an as a U32, of course. Perfect. And then the next thing, of course, is once we've finished with all of the columns of the row, we have to move down to the next row, which means we also have to update the left-hand sum associated with the rows by the row sums I as U32. And there we go. So now if we kind of break down that real quick, what's going to happen here is we're going to start on the 0th row and calculate the cost associated with the first element of that row. Then we're going to go through all elements, all columns in that row, and continue to recalculate the cost of each element by using this formula of the current cost or previous cost plus 2 times the accumulated sum of columns minus the grid sum. Once we've calculated a cost, we can compare it to the minimum to always take the minimum, and then we can continue to accumulate those columns. Once we're finished with this row, then we accumulate the row sum and move to the next row, and we do this for all rows and columns. And so by the end of this, we'll have calculated the actual minimum of all cells in the grid. So let's go ahead and see if this has worked out for us. So we'll go and open up a floating window real quick, and we'll just do a cargo run and pass in a restaurant. Ooh, can't do that just yet. My apologies. Let me go ahead and bounce back. I need to go and open up my mod. And let's go ahead and open up here a secondary restaurant opening for our Intuos solution, where now what we're going to say is this is our main Intuos. So there we go. Now we've connected Intuos into our build system. And now I can go ahead and say restaurant opening Intuos. I did misspell, so let me go ahead and put an R there. Restaurant opening Intuos. Go ahead and run that. That looks good. Let's jump over to restaurant opening and grab this input right here. So we'll say 1 and 10 and paste that in, and we get 591, 591. So it's already looking good. I really wish this particular problem had the solutions online. It does not, but that's okay. We'll go ahead and try uploading real quick. Let's upload the restaurant opening. We'll go ahead and clear off main here. We don't need that anymore. And we'll go ahead and make main into our actual main and submit. And let's see how well we do. Okay, and there we go. And this improved solution has in fact passed. Now, if we look at our prior solutions, right, you can see I've gone ahead and kind of worked with this a few times. There's no discernible difference in terms of running time for these solutions. We're seeing it doesn't measure to the, what is that, would be tens of milliseconds, right? So it doesn't measure there, but that doesn't mean we haven't vastly improved the performance of our particular algorithm. So now we can start talking about how we can actually bench this solution now that we know it's valid. I'm going to go ahead and make directory benches. I'm going to go ahead and add into that directory a new restaurant opening bench.rs. That's what we're going to go ahead and add into that. And if you've never benched in Rust before, there's actually a crate for it called Criterion, which is really, really cool. So Criterion Rust. And if we go ahead, I think we can jump, let's see, to the documentation on Criterion. Yes. So here is an example of doing a benchmark, in Criterion. It's fairly straightforward. All we're going to do is just do a cargo add -dev Criterion. So that'll go ahead and get that installed. Then we're going to go ahead and open up our cargo toml. And inside of cargo toml, we just need to add our benches. We'll come down here, we'll go ahead and add that bench. And so it says that the name needs to be equal to, and this is going to be our restaurant opening bench. Okay, no RS here. And then we're going to say harness equals false. Okay, so that looks good. So we can go ahead and save and quit there. Now we've got Criterion installed. We have the bench set up. Then we just go ahead and we take this right here. We're going to go ahead and open up our bench solution. So let me jump back over here and open up that bench. Then we're going to go ahead and paste all of this in here. And let's start working on this real quick. So first thing, we don't need the black box. We just need the criterion group, the criterion main, and the criterion. We don't need this Fibonacci. Instead, what's going to happen here, we're going to go ahead and delete this. We're going to go ahead and have our fin. We're going to have our in4 solve, which is our original solution. And keep in mind that our original solutions took input from standard in, which we don't want to use as a part of our benchmark. So all of these are going to assume that they're going to get a reference to a grid, which will be a reference here to a, in this particular case, we'll have it be a byte. So we'll still have them use, well, actually, let's go ahead and yeah, I know they need to use the same grid, so it'll be bytes. So this will technically be a slight improvement over our original solution, but that's fine. So there'll be a U8s, there'll be 50 of them, and then 50 of those, and they don't return anything. And then we'll have, from that, we'll also have our in2 solution. So we'll call that our in2 solve. And so then now we can do right here is we can go ahead and say this is our in4 solve. And then now we can go ahead and update this to be the in4 solve. We'll go ahead and also, by the way, we'll just go ahead and pass in an in usize and an m usize since we normally calculate that as well. So we'll pass that in. Perfect. Okay. And so what I'm going to need real quick is I'm going to need a new grid where the grid will be a, let's say 0 U8. There'll be 50 of those and then 50 of those. I'll need to let n and m be equal to 0 U size, 0 U size. Sorry, those should really be 50, 50. There we go. And now for the in4 solve, I can get rid of this and just pass in a reference to the grid n and m. And that should be fine. And then we'll go ahead and come down here and do our in2 solve, right? So we can pass in that grid. We can pass in and m. Let's go ahead and paste that above. But we do need to go ahead and calculate our grid real quick. So I'll go ahead and let that grid be mutable. And what I want to do is just fill it with random data. So if we want to do random data here, there is a ran package in Rust. So we come over here to Rust. Here are some examples of generating random data. There is a gen range, I believe, in this. So we can see here the rand RNG has a gen range. And so all we need to do is use the rand RNG. And we can actually then gen range on a particular range of numbers. So in this particular case, everything from 1 to 50. So I'm going to go ahead and quickly just bounce out of this. And let's do a cargo add -dev rand. Okay, so now that one's been added. I will need to actually jump out and then jump back in. So that way it'll update to use the rand package. And I can say rand RNG here. So now we've got rand in, and I can say for I in 0 to n, for j in 0 to m. And then what I want to do now is just have grid ij be equal to RNG gen range, right? So, RNG dot gen range. Am I missing? I need to get my RNG. So let's do let mute RNG be equal to, and this says thread RNG. So that means I also need to go ahead and get my thread RNG and RNG. Yep. Sorry, this should be capitalized. Perfect. So there's my thread RNG. And then we do the RNG.genRange. And then 0, 2, and then, or sorry, 1 to 50. Okay. And it looks like it did type in correctly now. So now we can fill in the grid with arbitrary data. We'll use the same grid for both the in4 solve and the in2 solve, passing in N and M. It definitely has 50 elements. So that's all looking good, right? And this won't be bench because it's not a part of the bench function. And yeah, so we are looking good there. So then all that's left now is to go into restaurant opening, right? Come over here to our first main function, and then we'll just go ahead and copy all of this code and copy that. Come over here and we're going to paste this in. And then I do actually need it to return something. So we're going to go ahead and have this return a U32 in this particular case. Okay. And then I'll just go ahead and have min cost be mapped to a U32, not a problem. And we can go through all of this code real quick. Sorry, let's jump up and let's go through this. So none of this is no longer needed because all of this is in M and grid calculations, which is all gone. And so now it's just the let mute min cost, and then all of this just iterating over all of those elements. Okay. Now the other thing though is for the in M, because of the absolute values here, we need to go ahead and say in as I32, and then we need to say M as I32, and then in as I32, and then M as I32. So that way it'll allow for the abs calculations. And then we have the mismatch types. And so then this needs to be an as I32. And I know that it's going to be doing this correctly, but I just want to be double sure. And then we've got the CMP minimum and then the cost here. Oh, wait, we don't have CMP declared. So we need to go ahead and use standard CMP. Okay, that's looking pretty good. What do we have here? Expected, right? So then we'll get rid of this print line and we just return the minimum cost. Okay, sorry, as U32. Okay, so there we go. So we've got that one in. So now let's go ahead and grab the next one. So let's do 12K there. So let's go and grab this solution. Yep, all the way down to here. And let's come over and now paste that into here. So again, in and M, we don't need that calculation, but then now things have to be slightly improved because before we were taking in all of this data in order to calculate our row sums and column sums and everything, but we're not going to have that data anymore. So we got to get rid of that IO standard line. We got to get rid of that buffer. We got to get rid of this buffer and the trim and the split and the map. But now what we can do is we can just go ahead and say here, I can delete this and I can say for grid I in, and then we're going to say grid.iter.takeIn. And then I need to also say dot enumerate. So we need to enumerate over that, enumerate.takeIn. And then this becomes now I and grid and I. Okay. And then now this becomes grid I dot iter dot enumerate dot take each. There we go. And so then we can go ahead now and put a reference on that, and that should clear up the rest. And this is one of the things I love about iterators in Rust. It's so amazing that we have this string iterator to take in our standard input, and then it's like a few things to just flip it around to have a completely different iterator and have all the rest of the code working exactly as it should. We just flipped from a buffer iterator on a string to just an iterator over a slice, and the rest of it just works the same. I love it. Just connecting iterators is so good. Then we got our min cost, then our cost, then all of these calculations, and then I do want to go ahead and return here our min cost, which means that I do need to come over here now and have this return AU32, but otherwise this looks good. Okay, so then with that, I should be able to just go ahead and save, come over here. Let's go ahead and make this a little bit bigger again. Clear this, and I should just be able to say cargo bench, and it should be able to just compile and show us what our benchmarks look like. There we go. So it's warming up in the N4 solve. And now it's warming up on our N2 solve. And there you go. So now we've gotten the results from our N4 solve and our N2 solve by an improvement upon the algorithm. And it says that our average score for the N4 solve comes in at 2.3138 milliseconds. So 2.3138 milliseconds, whereas our N2 solve comes in at 1290 microseconds. So that means that we have literally improved the performance of our solution by a factor of 1,000 times, right? Our N2 solve is quite literally 1,000 times faster than our N4 solve, which is amazing. That is a dramatic improvement, and it's because we're able to improve upon the algorithmic complexity of our solution. By the way, I've benched this before, right, in preparation for this, and I didn't get 1,000 times. Last time I did this, I got 200 times, but I also didn't make use of iterators, and I didn't make use of strict data types. So I am curious to see how much that actually helped our solution, right? Won't be going into that, but again, I hope that this was really interesting and helpful. I hope that it showed you some fun ways in which you can actually go about improving your algorithms. And at the very least, I hope that it shows that good ideas and creative ideas can lead to really dramatic improvements and some fun results. This has always been my most enjoyable, or rather to me, the most enjoyable part of competitive programming, is coming up with my own unique ideas to improve upon algorithms and then actually seeing the results of that work. And I hope that you can find opportunities to do that as well. That's why I have this channel to begin with. So anyway, that's basically all that we have for this episode. I hope that you enjoyed it, and I hope that I'll see you in the next one. But until then, have a great night.